most of the matches between Go programs that took place. Now things have moved to KTS, which is a server based in Portland, Oregon. So the first programs had to have their own, they were commercial programs, and they had to have their own built-in graphical user interface so that people could stand and play with them. And you basically loaded the software onto your computer and then played with it. But with the servers, clients began to be developed, and those were capable of interacting independently with the server or with the program or with the human. And so things changed, and they got a lot nicer when this happened. The modem protocol that I mentioned went out the door when a reasonable ASCII protocol was developed by Gunnar Parnevik with GNUGO. We had to get permission from Richard Stallman to use a different licensing for the particular files in the GNUGO distribution so that they could be used in a proprietary program. Most of the files are in places GPL, but the ones that operate the protocol are licensed BSD or X11, which means that they could be taken and put into a proprietary program. So there's a quick classification. So we could classify Go programs as commercial or research or free. I guess the first two categories are not mutually exclusive, and the last two categories are not mutually exclusive. But a commercial program is one that you can buy from somebody, and these are always closed source. The free-Go programs include GNUGO and also some stronger ones. Particularly Apache is the strongest free-Go program, and I'll come to these programs later. So a research program would be something like AlphaGo, which might or might not have source code available to them. So I'm going to talk about GNUGO for a little bit. So there was an article in Byte magazine about a program called Wally by somebody named Jonathan Mullen, and Man-Long Lee, who works for Microsoft, took that and wrote a free-Go program and got it part of GNU, which means it was distributed under under the GPL as part of GNU. Because it was open source, you could take it and you could start modifying it. And I noticed that it was capable of some obvious improvements, which would make it stronger. And what I didn't realize was that once you start doing that, you get sucked in, and it's like it takes over your life for a while. So anyway, I wrote a program called Liberty 1.0, and that program is still available on the internet. If you go to the KTS server, somebody in Finland is running a Liberty bot. I don't know the person that's doing that. So anyway, three things happened. I was contacted by Jan Vandersteen in Holland, who had his own program called Liberty, and he objected to the use of the name. I was contacted by Stuart Craycraft and Richard Stallman with the Free Software Foundation, and asked if we could take Liberty and make it into GNUGO. I was concerned that Man-Long Lee might not be happy about it, but he was okay with it, so we started working on it. I was contacted by another programmer named David Denholm. He worked for Citrix UK, and so we started working on it. We were unable to release our code because the Free Software Foundation required a copyright assignment, and they required it from not only David but also from his employer, Citrix. And Citrix was very slow about doing this, so the result was that we worked together without anybody else seeing our code for several months, and finally in April we got the Citrix software copyright assignment, and so we were able to release GNU-Go. And immediately, other people wanted to work on it. I'll mention Gunnar Farnabeck because he was probably the strongest programmer. He's somebody that works in computer vision, and he's very good. He had a lot of vision about how the program should be developed, and we made it into quite a respectable program, though still not at the level that a middle-level amateur program player would be challenged by it. It's a good program for beginners, and we had a lot of help from a lot of people. I mentioned a few of them. The development slowed after 2004. Gunnar got a job and he had a child, and even more than that, we started realizing that GNU-Go could not compete with the Monte Carlo programs, which I'll discuss later. So the last stable release was 3.8 in 2009. And there's still a Git repository. Somebody could start enhancing it with, but it would probably be better to start from scratch using a different paradigm. So now I'm going to show you some of the issues that face anybody this programming. So by reading, I mean search. In computer science, it would be called search, but reading means that you envision future positions in your mind, and you try to figure out what you can do. In chess programming, it was found that brute force search, that you search an enormous move tree. Evaluation of the terminal nodes in the tree is very easy, and so you can search an enormous tree, and you can basically find the best move by means of that. That was sufficient to beat Garry Kasparov. That doesn't work in Go. The reason is that in Go, evaluation of the terminal nodes of the tree is already a difficult task. So, at the terminal nodes of the tree, you will find that some of the groups on the board are alive, some of them are dead, and some of them are critical. If there's a critical group on the board, that means that life or death of that group depends upon who plays next. It may even be that there are adjacent dragons, one of each color, which are both critical, and one of them is going to die, and one of them is going to survive. And this is called semi-I. So the decision as to whether a group is alive or dead or critical itself requires quite a bit of analysis. This means that the evaluation of the terminal nodes in the tree is not trivial. So I'm going to show you an example. So I asked GNU-Go to evaluate the position in the upper left-hand corner. So this is a critical position. If white moves first, he can kill. If black moves first, then it's possible to live. The variations form a tree, which is displayed down in the right-hand corner. So the very first move, if you want to kill, is this one. And once the stone is placed, there's no way to live. Black can try this way, but there's no reputation. And this group does not have two eyes, which, if you know the rules of the game, means that it's dead. And even if you don't know the rules of the game, it means that it's dead. So there's no way for this group to live, and this sequence of moves shows that. There's a variation. Instead of going here, black can try to go here, but that doesn't work either. On the other hand, if black plays first, this move performs two eyes. It carves out two separate eye spaces in the corner, and consequently, there's no way that this group can be killed. So GNU-Go can figure this out, not too inefficiently. How does it do it? Well, it has to find the right move. So, for example, here, it has to find this move. And the comments here tell you what GNU Go did. So I wonder, is that very readable? Oh, okay. Well, I'll show you what it says. So first it says A1303. Okay, so now if you look in the GNU Go source code, there are many patterns which are encoded graphically like this. These were written by hand, then they're compiled to C. The X's mean black stones, and the O's mean white stones. The question marks means that the color of the stone is irrelevant. The star is the move which is proposed by this pattern, and if this pattern is found, then that move will be tried, and that's what happened. So the problem with this is that all of these patterns were hand-coded by people that were analyzing GNU Go's games, finding its mistakes, saying, well, this it would play correctly if we change this pattern here. There's a test suite in which we run a bunch of tests, and things that have been fixed in the past. If something else we do breaks them, then tests are going to start failing, and we'll find out that there's something wrong with the pattern that we've added. And this is time-consuming, and is also of limited success. This is perhaps not the way it should be done. It works up to a point. Okay, so this is what I have to say about reading. The other thing I want to talk about is influence. I'm going to use one of the AlphaGo games in order to illustrate this concept. So the ability of a group to live inside some region depends a lot upon the surroundings. If the opponent has a lot of walls in the vicinity of that stone, then it may be difficult to live. And so we have sort of an intuition that, let's take this in. This is a third AlphaGo Risadal game. So I want to look at the bottom here. This region in the bottom is AlphaGo is white. White's influence in the bottom is very strong because it's completely surrounded by walls. Black could try to go in, and perhaps Black could make life in it, but it's very unlikely. Nevertheless, Risadal invaded there, and this is because he knew that he was behind. He started to go in. And the fact that White's influence is so strong means that this is a very bold and courageous thing to do. So he makes a forcing movement, and AlphaGo doesn't even answer. It plays up here. The influence is so strong that it doesn't look like there's any way that Black can make life. Nevertheless, Black was able to make what's called a toe, which is a kind of a situation where the life and death depends upon the outcome of a fight that may globally involve other parts of the board. So this was quite a success for Risadal, was to make this toe. Unfortunately, it wasn't good enough because he was not able to win the toe. When I say that a toe depends upon other things that happen in other parts of the board, the rule of toe, this stone has just been captured here. The rule of toe says that Black may not immediately recapture it. If he doesn't recapture, a White can still there and win the situation. But since he cannot immediately capture it, the rule of toe says he has to do something else. So he goes over here. He makes a toe threat. A toe threat is a move in perhaps another part of the board which has to be answered because the gain that you would get from killing something over there would be adequate compensation for losing the code. So AlphaGo answers it, and so the code fight continues. Unfortunately, AlphaGo had a local code threat local to this situation, and Lee Sedol realized that he did not have enough code threats outside, so he resigned. I'm going to digress a little bit to show you part of the game, but I want to make the point that influence, meaning sort of the sense that these white stones, if I do this, you can see, these white stones sort of radiate a power that fills up the space. That's our intuition. But somehow capturing that idea is an important issue in Go programming. So we need to have an influence function. So I'll go back to the influence function first appeared in the very first program in 1968, this program of Albert Zobrist. And this is, maybe I can show you, here I'm running GNU-Go, and I'm asking it to do a bunch of analysis and show me the results. So it generates a whole bunch of different diagrams, of which this one shows the status of the groups, what it believes is alive and dead. It believes this group up in the upper corner is critical, but in fact, Lee Sedol is alive up there. GNU-Go has that evaluated wrong. This shows the influence. So you can see at the bottom here that so the influence is actually a number. The green is very strong influence, but then other colors, red means a low amount of influence. Yellow means a medium amount of influence. The influence function is intended to capture the intuition that these white stones are radiating some quality which controls whether it's possible for black to live or die inside. Up until around 2006, all Go programs, we believe, work more or less the same way. Of course, we haven't seen the source code to the commercial programs, but we have some idea how they work. Really, I kind of showed you that there's hand-coded patterns which determine the reading, and there's an influence function, and all of these programs probably are very similar in architecture. But then the Monte Carlo